Hi class, good morning. Welcome to the continuation of the lectures on quantum mechanics. And again, I'd like to uh, give, give to reiterate our reference, Introduction to Quantum Mechanics by David J. Griffith. So please, you buy this book if you have extra resources, because it's really worth it. You know all the details of this lecture, because most of the materials that's in this lecture is taken from this reference. So there's by the way, a problem here. Before we're going to discuss the eigenvectors and eigenvalues. I'll just read to you the problems. The problem for the previous lecture. Show that the rows and columns of a unitary matrix constitute or an orthonormal sets or orthonormal sets. You know the meaning of orthonormal, right? And you also know the meaning of unitary matrix. So let's now proceed with eigenvectors and eigenvalues. These are characteristics of a matrix, the eigenvectors and eigenvalues. So when you do transformation, like for example, you want to rotate an axis, in Cartesian coordinate, there are x, y, and z axis. So if you want to rotate an axis, changing the orientation of, say for example, you rotate the x-axis, so you change the orientation of the y and the z axis, and so it's now having an angle with respect to the original. That's one transformation. Or you can also do other transformation, like changing x to negative x, leaving the y as is, and change the z to negative z. So those are transformation. But our transformations, these transformations have characteristics, and these characteristics are given by their eigenvectors and eigenvalues. So this so these transformations you can apply to a vector. Alpha will have components a1, a2, a3, a4, and so on. So you just have to do the transformation. So there are also transformations, like if you rotate in a way that the theta is 180 degrees, then the transformation would just be giving you a vector that is negative of the original. So anyway, the transformation T is represented by a matrix T, and the matrix T, if your original vector is like 3 components or 3-dimensional, your matrix T, or the transformation that is in the matrix that's representing the transformation T. This is a transformation T. Transformation has a hat, so it's a transformation T that is represented by a matrix T. This one, that's represented by that. And if your vector is 3-dimensional, that means it has three components, that the matrix that represents your transformation is 3 by 3 matrix. So for this transformation, um, looking at this, um, there are special vectors, and these vectors can be multiplied to a to a to a value we call. These are also special values called lambda. They are actually eigenvalues, and the vectors are called eigenvectors. They are characteristics of the matrix. And when you multiply the eigenvector to its eigenvalue, and when you subtract that eigenvalue times eigenvector to the matrix times its multiplied to the eigenvector, it will give you 0. So anyway, let's look at this. Um, Eigenvectors are non-zero, means that the components of the eigenvectors are not 0. No, any non-zero multiple of eigenvector is an eigenvector with the same eigenvalue. So here in this equation, um, you have lambda here as an eigenvalue, and a as an eigenvector. You can find through this equation. So um, this one here is just an identity matrix. So if you transpose this or transfer this lambda a to the other side, it would just be equal to t minus lambda times 1, the identity matrix. The whole thing multiplied to the vector a is equal to 0. Here 0 is the 0 matrix, so elements are all 0. So what does the matrix look like? So the matrix with elements all 0 has determinant 0. So the determinant of a 0 matrix is also 0. So if you get the determinant of this side, the determinant of t minus 1 lambda, these are the components of lambda, or the elements of the lambda. I mean t minus lambda 1, t11 minus lambda, t12, and so on until t1n. And in the second row you have t21, t22 minus lambda, and so on till t2n. For the third row you have t31, t32, and then the third term would be t33 minus lambda and until t3n, and so on. So only the diagonals are subtracted with lambda in this case. So again, we are discussing eigenvectors and eigenvalues. The matrix has its own eigenvectors and eigenvalues. These are characteristics of a matrix. And the transformation is represented by a matrix. So we're now looking at the eigenvalues and the eigenvectors of a matrix. So if you expand this, you'll get an equation that looks like this. This one. The determinant is, of course, you know how to do that in 3 dimensions. You know how to do that. You can extend that to 4 dimensions, 5 dimensions, and so on. And this equation that can be derived from here is called the characteristic equation of the matrix. And from that characteristic equation, you can derive the eigenvectors and eigenvalues. So for n by n matrix, the characteristic equation is an nth order equation, and it has n complex root. It has n complex roots, but these roots can be repeated, or some of these roots are duplicates of each other. So if one root is 3, then as you solve the equation, you can also find 3. Those are called roots of the same value, or degenerate roots. So the characteristic equation, this is an nth order characteristic equation. You have Cn lambda to the n, Cn minus 1, lambda to the minus 1, plus, and so on until C0. This is equal to 0. Um, it has at least 1 and at most n distinct values. The roots could also be the same value, so that you will only have one value for the roots. But the roots could also be different values. So it has at least 1 and at most n distinct values. So let's do an example for you to understand better what I have just said for eigenvalues and eigenvector. Now let's do this. Find the eigenvalues and eigenvectors of this matrix M, which has elements in the first row 2, 0, negative 2. Then for the second row, negative 2i, 2i, 1, 0, negative 1. So I usually read my matrix per row. So when I say M matrix 2, 0, negative 2, negative 2i, 2i, 1, 0, negative 1. So that's how I read my matrix. Maybe you read your matrix differently, but that's how I read it. So, but anyway, you can see the matrix. That's M, which has 6 elements. The characteristic equation here is given by this matrix. You have to subtract the lambda. The lambda actually signifies your eigenvalues. That's just here. This is the n-dimensional extension of that. We're only dealing with 3 dimensions in the example. So all you have to do is subtract lambda in the diagonals in this matrix. So you have to subtract lambda in 2, subtract lambda in I, and subtract lambda in negative 1. And so when you get the determinant, you have the determinant of this would just be negative 2 minus lambda times this quantity minus this quantity. And then 0 and negative 0 times this quantity minus that quantity. And then you have negative 2 times this quantity minus that quantity. I know you have experienced that before. And so you have this characteristic equation. So this is negative 3, negative lambda to the cube plus 1 plus I lambda square minus I lambda equals 0. And its roots are 0, 1, and I. So so here you have now the roots are called the eigenvalues, and each of these eigenvalues, you have 3 eigenvalues: 0, you have 1, and then you have I. 3 eigenvalues. We call this component we call this we did not choose these eigenvalues. It comes from the determinant of this matrix. This is a characteristic of the matrix. And each of these eigenvalue will correspond to an eigenvector. So the eigenvectors are the eigenvectors are represented by this. It has three components: A1, A2, and A3. So this comes from here. This comes from here, 3.69. So that one, this is your original matrix times the eigenvector times the first eigenvalue, which is 0, the first eigenvalue, times the eigenvector. So if you multiply 0 to all components, that will give you everything 0. So these three equations this yields your three equations. So you have a times 2 in a1 times 2, which is this one, and then a2 times 0. So there's a 0 here. So a3 times negative 2. So your first equation would be 2 times a1 minus 2 times a3 equals 0. Because if you multiply this column to this row, gives you 0. The next one, a1 times negative 2i, this, which is this one here, and then a2 times I, which is this one here, then a3 times 2i, which is this one. That is also equal to 0. And then a1 times 1, this is a1. A2 times 0 is just 0. So a3 times negative 1 is negative a3 equal to 0. So in this case, look at the first equation here. This one here, first. So you can say that a3 is equal to a1. And the second determines a2. Here, a1 and a3 are the same. A1 and a3 are the same, so this can cancel, and then you will have a2 equal to 0. So now you know these, and you know this. Now, if we pick a1 equals 1, if we pick a1 equals 1, or you can pick a1 equals 5, or a1 equals 100 or 1000 or 1 million, but we just pick a1 equals 1 for simplicity. Any multiple of an eigenvector is still an eigenvector. So we just pick a1 for a1 is equal to a1 for simplicity. And you can pick anything for as long as if a1 is equal to a3, if a1 is equal to 1, then a3 should also be equal to 1. Not a1 is equal to 2 and a3 is equal to 5. You know that a3 is equal to 1, so you have to have this vector 1, 0, 1. This is your eigenvector. This is not a normalized eigenvector. This is just an eigenvector, but a normalized eigenvector would be having a norm that is equal to 1. So this one, the magnitude of this is 1 squared plus 0 squared plus 1 squared, which is equal to 2. The square of the magnitude. So the norm would be the square root of that. That's square root of 2. So you have to multiply 1 over square root of 2 here to get a normalized eigenvector. So anyway, let's proceed. For the second eigenvector is 1. The second eigenvector is 1. So you have this original matrix and this eigenvector times 1 times the eigenvector. So if you multiply 1, if you multiply 1 to a1, 1 to a2, and 1 to a3, you will get this. Unlike here, when you get all 0 because the eigenvalue is equal to 0. So here you have a1, a2, and a3. And then when you when you use the same equations here, um, 2a1 minus 2a3 will now be equal to a1. And then the second line would now be equal to a2 here. And the third line would now be equal to a3. So in this case, you have, um, if you transpose 2a1 to the other side here, it becomes negative 2a3 equal to um, negative a1. Because it's negative 2a3 is equal to a1 minus 2a1. So negative 2a3 is equal to negative a1, and that means you have negative 2a3 equal to a1, equal to negative a1. So that your a3 is equal to um, 1/2 of a1, as given by the first equation here. Now, um, the second equation gives you, so a1 is 1/2, a3 is 1/2 of a1, or so you can write a3 here in terms of a1, and so you can get a2 in terms of a1, and then of course you know what a3 is. A3 is just 1/2 of a1. So if you pick a2, equal, I mean, if you pick a1 equal to 2, then your eigenvector would be 1, would be 2, and then you substitute a1 to a1 here, substitute 2, and then you get 1 minus I, and then of course a3 would just be 1/2 of a1, so 1/2 of 2 is just equal to 1. So this is your um, eigenvector. This is for lambda equal to. This is for lambda equal to 0. This one, this one is for lambda equals 1. I'm sorry. So this is the eigenvector associated with the eigenvalue 1. And of course, this is not normalized. How do you normalize this? Get the norm. 2 square plus 1 minus I square is what? This is 4. So 2 square is 4 plus 1 minus 1. 4 plus 1, 7, 9. So square root of 9 would just be equal to 3. So the normalized eigenvector here would be 1 over 3, 2, 1 minus I, and 1. So finally, for the third eigenvector, we use the third eigenvalue, I. Use the third eigenvalue, I. And so what happens? You have you have 2, 0, 2, 2i, 2i, 1, 0, negative 1 times the eigenvalue, eigenvector for the third eigenvalue. The third eigenvalue is I, so if you multiply I to a1, a2, a3, you will have I a1, I a2, and I a3. And this will give you, wait for a while. So for this equation, for this first equation, you will have 2a1 minus 2a3 equal to ia1. How can this be? The only way that 2i1 could be equal to ia1 is when a1 is equal to 0, because there's no I in this side and you have I on this side. So a1 should be 0. And if a1 is 0, then a3 would also be 0. So that's what you get for this characteristic equation, or for this equation A1 here. And the 2, A1, this is 0, this is 0, and then you're left with I2 equal to, you're left with IA2 equal to IA2. So IA2 is equal to IA2 for whatever values of A2, uh, the equation works. So you can just pick out A2 equals 1, and then you will have this eigenvector. So anyway, A1 is 0, A2 is 0, this is 1. Well, you can pick anything, any number, but for simplicity, you can just pick A equals 1. You can pick 1,000 or 500 or 1,000,000, but for simplicity, you can pick 1, and then this is already normalized vector. If you this is for lambda equals I, the eigenvector, the eigenvalue I. So for each eigenvalue, 1, 0, and 1, 0, and I, you have 3 eigenvectors. These are the eigenvectors for for eigenvalue 0, and this is the eigenvector for eigenvalue 1, and this is the eigenvector for eigenvalue I. So there are 3 eigenvalues, and there are 3 different eigenvectors corresponding to each eigenvalue. So you can find that. This one is not normalized, so you just get the norm of this, just divide with the norm. And this one is not also normalized. So if you want to normalize, just divide with the norm. What is the norm here for the third one? This is already normalized because the norm is 0 square plus 1 square plus 0 square. So you have 1, and then square root of 1 is just equal to 1. So this is 1 over 1, 0, 1, 0. So it doesn't change anything. So your vector is already normalized. But if you choose another number here equal to 5, for example, this is 0, 5, 0. The normalized one would be 1 over 5, because that would be 0 square plus 5 square plus 0 square, and the square root of 5 square is equal to 5. So 1 over 5. So it will still reduce to 0, 1, 0. So that's how you get the eigenvectors for different eigenvalues of a matrix. So there's a note here. If the eigenvectors, this is eigenvectors, sorry. If the eigenvectors span the space, they can be used as basis. They can be used as basis of the space. So for example, in 3 dimensions, it's not only ijk. Of course, ijk span space, the 3-dimensional space, but there are also other vectors that span the space. They couldn't be just ijk. These eigenvectors, if you write it in rows, these are just the components of the 3 vectors. You can also use that as the vectors instead of ijk. So if they span the space, they can be used as basis. Only if the eigenvectors span the space. So if you get the transformation times the eigenvectors, it's just equal to I1 lambda 1 f1 So this is just the same thing as here, what I'm doing here. So this is the transformation. In this case, the transformation was the in this case the transformation was represented by n here. So um, with the eigenvectors as the basis, your transformation is simply um, written in this form. You don't have a very messy transformation matrix because you can only write all the eigenvalues on the diagonals here. So in this case, the m here, the transformation m, you can change this to 0, 1, and I, and put all other elements to 0. So this, you can write this as 0, 1, and I, and the other terms equal to 0. Because that is if they span the space. The condition is that if they span the space. So you can write the transformation equal to this. And of course, the normalized eigenvectors are equally simple, and the A1 would be 1, 0, and everything, 1 and everything 0. Then you have A2 is 1, 0, 1, 0, everything. And up to n, an would just be 0, 0, 0 until 1. So a matrix can be brought to diagonal form by a change of basis is said to be diagonalizable. So if you have a matrix, in this case, for example, in this example, you have this matrix. You can transform this into a diagonal matrix, which is you can write like this with the lambda, with the eigenvalues. So I hope you understand what's going on in here to find the eigenvalues and the corresponding eigenvectors. So that matrix is diagonalizable. You have the diagonal form of the matrix by writing all the eigenvalues on the diagonals. So what is a similarity matrix? You have a similarity matrix, say for example, you have so you have eigenvectors here 1, 0, 1, 1, 0, 1, 2, 1 minus I1, and 0, 1, 0. You can construct the similarity matrix. You have here, say for example, you get the inverse. You can construct the inverse of a similarity matrix as 1, 0, 1. Note that these are the eigenvectors. These are the eigenvectors 2, 1 minus I1, and 0, 1, 0. So these are the three eigenvectors. The first column is the first eigenvector. The second column is the second eigenvector. And the third column is the third eigenvector. And this is the S inverse. We call this S inverse. To get the inverse of this S inverse is you do the process which we're discussing in the previous lecture. You'll be able to find this inverse of the matrix. You can also use software in the internet to get the inverse of the matrix. However, it's good to do it's good to know the basic process and how to get the inverse of the matrix before you go and use an app. So um, now you can diagonalize. You can multiply this matrix S here multiplied to the M here. You can do this on your convenient time, M, and then you can put the S here. So you have multiplying three matrices. First, by the way, in multiplying matrix, you have to do it from right to left order. So first here, S1, first is S1, and then the M, the original matrix here, the original matrix here, and then the inverse matrix here, S. So, and then you can get the diagonal form of the M. So the diagonal form of the M is just 0, 1, I. No, but 0 is an eigenvalue, 1 is an eigenvalue, and I is also an eigenvalue. And the rest of the elements in the matrix are 0. So in this case, you have successfully diagonalized M. So you have an M original matrix, and then you have a diagonal matrix here, just composed of the eigenvalues of the matrix. And the S inverse is composed of the eigenvectors of the matrix. So you can construct S inverse and then you can construct S. But there's a note here. Unfortunately, not every matrix can be diagonalized. And you can find that out. There's a problem here, which you can do. The 2 by 2 matrix representing a rotation in the xy plane is given by this. And you can then manipulate this using this matrix. You can get the eigenvalues, and then from the eigenvalues you can get the eigenvectors, and then construct the S, which diagonalizes the T. Or first you can construct S inverse. You can do this, S inverse. So in this case, it's very simple because this is just 2 by 2. The determinant will just be cosine square minus negative cosine square, which is just equal to 1. So in that case, it's very simple. Here, find the eigenvalues and eigenvectors of the following matrix, and you can also check if this matrix can be diagonalized. The next problem is show that the first, second, and last coefficients of the characteristic equation are given by this. This is kind of challenging, but you can solve this. There's problem 20. You can screenshot this and maybe think, not solve, but maybe think, realize how to solve this problem. Note, in problem 20, the determinant of a matrix is equal to the product of its eigenvalues. Look at this. The determinant of a matrix has the product of its eigenvalues. And the trace, by the way, the trace of a matrix is the sum of its eigenvalues. Of course, the trace of the matrix are the sum of the diagonals, the elements in the diagonals. And if that matrix is diagonalizable, then the trace will just be the sum of the elements in the diagonal for any matrix. For any matrix. So in everything, you have to get the characteristic equation. Of course, the characteristic equation can be written. Of course, this is the characteristic equation, and this is just the generalized. This is just the generalized characteristic equation. So we now go to Hermitian transformation. So there are transformations. We know that we can transform a vector, but is that transformation Hermitian? The condition is that when the transformation matrix, the matrix representing the transformation, if its Hermitian conjugate, if it has an adjoint or a Hermitian conjugate, then it must follow this condition that the Hermitian conjugate of the transformation, by the way, T is represented by the matrix, T hat is represented by the matrix T, T, and that's operating on a vector alpha B, must be equal to the alpha inner product of alpha times the transformation of beta. So if T is Hermitian, then you can transfer T from one vector to another. But if you transfer T to this side, you have two. I mean, if you transfer this T adjoint to the other side, beta, then that's just T hat. You don't get the adjoint. The adjoint means this. We have learned that in the previous lecture. So, by the way, note that these are the meaning of the notations here. Transformation of beta means also the same as this one. I mean, the vector transformation beta is equal to transformation of the vector beta. And of course, this one means the inner product of this vector and of this vector transformed alpha, the Hermitianly transformed alpha with the vector beta. So that's just what it means. By the way, for any scalar C, for any complex scalar C, the inner product of alpha C beta, C is just a scalar. You can take C out of the inner product. But if C is located here, but if C is located in front of alpha, this will just be equal to C conjugate of C times alpha beta. This means that all the i's in C would have to be changed to negative I. So again, this is just the T is represented by matrix T. So you have the inner product in terms of matrices is this one. You have alpha here represented by a column matrix, and this is now a row matrix, and the B is a column matrix. A column means vertical matrix. A row is a row. Row matrix is a vector written horizontally. So this one is A adjoint TB. B is the matrix representing beta, and A is matrix representing alpha. So you have A adjoint. Uh, you can interchange the order here. You can interchange the order so that you can write this as the adjoint of T adjoint A, and this is just equivalent to T alpha beta. So in quantum mechanics, we usually in quantum mechanics we usually do this. We do Hermitian transformation. It's very important, not just the transpose or not just the conjugate of the matrix, but the combination of the transpose and the conjugate, which is Hermitian. Because Hermitian transformation have um, that importance in quantum mechanics. Some of the transformations that we do are Hermitian. So, by the way, the eigenvectors and eigenvalues of a Hermitian transformation have three properties, distinct properties. The eigenvalues of a Hermitian transformation are real, meaning it has no I component. It doesn't contain the negative square root of -1 or I. So that's just that. You can see the proof here, but just deal with this statement. The eigenvalues of the Hermitian transformation are real. You can prove it, and the proof is very short, but just deal with this. The next property is that the eigenvectors of a Hermitian transformation belonging to distinct values are orthogonal. So only Hermitian transformation have eigenvalues and eigenvectors that are orthogonal. Orthogonal meaning if you get the inner product of two eigenvectors, the inner product is equal to 0 always. So that's the second. You can prove it. You can prove it. The proof is very short. That this is the proof of that. But just deal with this. The eigenvectors of a Hermitian transformation belonging to distinct eigenvalues are orthogonal. By the way, distinct eigenvalues meaning they are different values, because sometimes the eigenvalues are of course the same, and those are degenerate eigenvalues, and they give the same eigenvectors. So of course they are not orthogonal but parallel. But for distinct eigenvalues, the eigenvectors are orthogonal. Distinct meaning they are different values. By the way, you know, we already had an example of getting eigenvectors and eigenvalues, so I hope you're not confused. The third one is the eigenvalues are the eigenvectors of a Hermitian transformation span the space. This is the most important thing in quantum mechanics. The eigenvectors of a Hermitian transformation span the space, meaning whatever vector that you can find in that space can be written in terms of the eigenvectors. Example of a vector that span the space is ijk. Ijk span the three-dimensional space. And of course, every vector in three-dimensional space, you can write it in terms of ijk. Ijk is just 1, 0, 0, 0, 1, 0, 0, 0, 1 for the ijk unit vectors. So let me just read the comments here. If all the n roots of the characteristic equation are distinct, then by property 2, which is this property, we have an n mutually orthogonal eigenvectors. So they obviously span the space if the roots are distinct. So that's the comment. Now, but the question is, what if there are duplicate roots? What if there's another root that is, like, for example, if you have a root equal to 2 and then suddenly you find out that for another eigenvalue, the eigenvalue is also equal to 2. So you will now have two eigenvalues that are equal to 2. So what do you do with that? Uh, what if the eigenvalues are duplicates? Or now these are called degenerate eigenvalues, as I've said. And suppose one eigenvalue lambda is m-fold degenerate. M-fold degenerate meaning it repeats m times. Any linear combination of two eigenvectors belonging to the same eigenvalue is still an eigenvector with the same eigenvalue. So you will now have m linearly independent eigenvectors with eigenvalue lambda. So you will encounter this when you have a matrix that's when you solve a matrix and you found out that there are degenerate eigenvalues. You will encounter this, and then what you do is that if you encounter that, because those vectors are not orthogonal to each other, you do the Gram-Schmidt procedure. You do the Gram-Schmidt procedure, and this Gram-Schmidt procedure is discussed in the previous lectures, and so you'll be able to do this. If you go back to the previous lecture, there's a problem there that discusses about the Gram-Schmidt procedure. You do it on your free time or your convenient time, then you'll be able to do it also for if you have degenerate eigenvalues. So, and also Hermitian matrix, you can uh, diagonalize it by similarity transformation. You can always you can uh, do diagonalization of Hermitian matrix, and that makes life easier to deal with those kinds of transformation. You have for this section, you have these following problems. You can you don't have to solve the problems, but you just get the essence of the problem and know the possibilities of solving the problems. Know the steps. Just, I mean, you don't have to solve it, but know how it is solved. At your convenient time, you can also solve 3.22. Do 3.22. Verify that this is Hermitian. Of course, you can see that it is, but can you find its eigenvalues? You can find the normalized eigenvectors and so on. And you can also do this for this matrix. You can do the things here. And there's also another problem here, 3.24. And in 3.24, you have a unitary linear transformation. You have a unitary matrix such that the Hermitian of that matrix, I mean the adjoint of that matrix is Hermitian conjugate, I mean, multiplied to the original matrix is equal to 1. That's called unitary. Unitary matrix are different from identity matrix. Unitary matrix is that you have the Hermitian conjugate times the original of the matrix is equal to 1, while the identity matrix is a matrix with diagonals of 1, and all other elements are equal to 0. So that's it for this session. Next meeting, we will be discussing about function spaces. Function spaces are different kinds of vectors. These are polynomials. Um, because like in the 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 things that we discussed previously, you have discrete kinds of vectors. You have directions also represented by e1, e2, or bases represented by those things. But in these function spaces, we'll be dealing with polynomials. So of course we'll be talking about sum of two functions. Is the sum of two functions a function? The answer is yes. The addition of functions is commutative and associative. The answer is also yes. Is there a null function in which when you add that function to a function gives the it, when you add a function to a null function gives the function? Yes. Multiplying a function by a complex scalar gives another function? Yes, also. So um, function functions can also be treated as vectors. So anyway, many of the most of these things will be discussed in the next lecture. So that's all for now. I hope that you'll be able to do your assessments and submit um, next week. Okay. So see you next week.